So this is the third lecture out of chapter 2. So in this lecture we'll cover some basic terminology in the class, particularly as it pertains to the periodic table, and we'll look at how to balance chemical reactions. Okay, so if you want to be successful in chemistry, then you have to learn to speak the language. So I kind of view learning chemistry similar to learning a foreign language. So if you were taking a Spanish class, for example, you'd probably want to know how to say uno, dos, tres, how to count in Spanish. Or if you wanted to order a beer, that would be cerveza, right? Or I took a year of German in high school and 2 years of German in college. So if you wanted to order a beer in Germany, you would say das Bier. Of course, most of you are not 21 yet, so this is not relevant, but maybe one of these days you'll want to enjoy a beer with a pizza or a hot dog or something like that. Or how to say hello in Korean. Hopefully I did that correctly. Or to a chemist, so NO3. So to most people, that's just 2 letters and a number and a negative sign, but to a chemist, NO3 minus means nitrate, right? So that's the language of chemistry. So if you want to do well in chemistry, you have to learn some of the language of chemistry. And that just takes pure memorization, just like if you were trying to memorize words in a different foreign language. Well, chemistry is a foreign language for most of you. Okay, so we're going to look at some of the language of the periodic table. So the periodic table was developed in 1869 by a Russian chemist named Dmitry Mendeleev. So basically what he figured out is that when you arrange the elements by their atomic weight, elements could be placed in rows and columns such that elements in the same column had similar chemical and physical properties. And that was significant because that realization that elements in the same column had similar physical and chemical properties made it easier to discover other elements. For example, if you knew if fluorine, bromine, and iodine had been developed, but this element in between them had been discovered, but that element in between them had not been discovered yet. Well, if you knew how fluorine, bromine, and iodine reacted, and their basic physical properties, then that will let you to know what to look for in an unknown chemical that may undergo similar reactions or have similar physical properties. Okay, so with regards to the periodic tables, there's lots of terminology that you should know. So first, what is a period? So a period are the rows. So that's period 1, period 2, period 3, 4, 5, 6, and 7. So periods means rows. And groups would be the columns. Okay, so groups are the columns. And if you notice on the periodic table, the way groups are numbered, you either have 1, 2, 3, on over to 13 and on over to 18. So 1 through 18 is one way that groups are numbered. So that is not the designation that I'm going to use. The one that I prefer and that most, well, I should say at least organic chemist, I'm an organic chemist, is this AB designation. So 1A, 2A, and then 3, 4, 5, 6, 7, and 8A. So you have this 1A through 8A designation, and then these here have these B designations, so 1B through 10B. And so that will be the designation that I primarily use. So if I say an element is in group 3, I'm talking about that one, group 3A. If I say an element is in group 7, I'm talking about that one. I'm talking about 7. That's not 7, that's 6. If I'm talking about 7, then I'm talking about that group, right? Group 7A is what I mean. Okay, so main group elements. Main group elements would be these 1A, 2A, and then all of these. So those are the main group elements. So that's the elements in groups 1A through 8A. And then the transition elements would be these. Whoops, we don't want to do that. So these would be the transition elements. Okay, so the inner transition elements, that would be the lanthanides and actinides. So the lanthanides would be here. So these would be the lanthanides, and the actinides would be there. So those 14 elements across the bottom of the periodic table are the lanthanides and actinides. Okay, so some other designations. So you have the alkali earth metals, or so the alkali metals. So that's going to be these elements. So group 1A. So except hydrogen. So on the periodic table, hydrogen is wrote here, but it is not an alkali metal. So you also see hydrogen is wrote here. It's in two places in the periodic table. Why is it in two places? Kind of gets into the chemistry it undergoes, and we'll talk about that later. But it is not an alkali metal, even though it's in group 1A. So the alkaline earth metal, or the group 2A elements. So that would be these elements, would be the alkaline earth metals. Okay, and then we have the halogens. So what color do we want the halogens to be? They can be whatever color that is, brown. Oops. So that would be group 7A. So these would be the halogens. So fluorine, chlorine, bromine, iodine. So not hydrogen. Hydrogen, even though it's in group 7A, it is not a halogen. Okay, so chalcogens are not very commonly known. So this would be group 6A. So that would be these. Those are the chalcogens, oxygen and on down. And then the noble gases. So noble gases can be orange. So this is group 8A. So hydrogen, neon, or helium, neon, argon, krypton, xenon, and radon would be the noble gases. Okay, so metals, nonmetals, and metalloids. So let's take the metalloids first. So the metalloids. So these elements, so this is the periodic table we typically use here at A&M Commerce. And this would be the one that I'll give you to use on exam. So the metalloids, you can see these elements are kind of in this bold. And depending on which periodic table you look at, some periodic tables classify different elements as metalloids. So we won't be that particular just because it's kind of a gray area of what would be classified as metalloid and what is not, but it's basically just stair step down that area of the periodic table. Okay, so then the metals will be everything to the left of the metalloids. So what do we want to make the metals? Okay, so the metalloids then, or the metals would be everything on this side, would be the metals. And then everything to the right of the metalloids would be the nonmetals. So we'll go in the other direction. So then this way would be the nonmetals. So everything to the right of the metalloids. Okay, so that's just some terminology for you to know. So what is the difference between a metal and non-metal metalloids? So later in the semester we'll talk about specific properties of these different elements. We'll get into some of the chemistry that they undergo. But in general, metals are generally, they can be soft. Some metals like sodium, you can cut it with a butter knife. Some metals are extremely hard like iron, right? They have characteristic luster or shine. So all of the metals are solids except for one, and the one that is not a solid is mercury, right? Mercury is here in the periodic table, so that is the only metal that is a liquid. All of the other metals are solids. They are malleable. What does that mean? That means they can be hammered into sheets, and they're ductile. What does that mean? They can be drawn into a wire, so like copper wires is very commonly used. And the nonmetals, so they're also very good conductors of heat and electricity. So the nonmetals are basically opposite. So everything in this part of the periodic table, the nonmetals, not very good conductors of heat or electricity. Are they solids, liquids, or gases? Well, kind of a mixture of all of them. Carbon, for example, phosphorus are solids. Nitrogen, oxygen, fluorine, chlorine are gases. Bromine's a liquid, iodine's a solid, so you have a combination of all of them. How about the noble gases? What do you think they are? Would they be solids, liquids, or gases? Well, obviously they would be gases, right? Because they're called the noble gases. So helium, neon, argon, krypton, xenon, radon are all gases. Okay, and so the metalloids basically have properties, some metal-like properties and some non-metal-like properties, and they can sometimes depend on temperature. Okay, so that's some of the basic terminology that you need to know, and so this is the easy part of chemistry, just pure memorization. So you either choose to invest a little bit of time to memorize what a halogen is, or you don't. And if you don't, then you're just guessing on a test. So for example, maybe you see a test question that asks you, what is the symbol of the halogen in period 3? So if you don't know what a halogen is and you don't know what period 3 means, then you're just guessing, right? How many elements are there in the periodic table? There's 118 elements. So if you don't know what those terms are, then you have a 1 in 118 shot chance of getting that question right. So the odds are not very good. Okay, so what is the halogen? So we're talking about group 7 here. And so this is period 1, this is period 2, and this would be period 3. So that would be chlorine. All right, so chlorine would be the halogen in period 3. So if you know these terms, that is trivial question on a test. The alkali metal in period 2. Well, so if you know that so this is period 1, this is period 2, and if you know that the alkali metals are this first group, so that would be lithium Li. So I'm not going to expect you to know the names of all of the elements on a test. You would have a handout that lists all of the names of the different elements, but you do have to know these terms: what alkali metal means, what a period means, what a group means, halogen, or right. Okay, or you may see a question like this. So circle the chalcogen in this list of elements. So this is an easy question if you know that here in gray, right, are your chalcogens. So oxygen, sulfur, selenium, tellurium. So potassium's a group 1 metal, it's an alkali metal, iron's a transition element, sulfur is a chalcogen, right? Bromine is a halogen, neon is a noble gas, so the sulfur is the only one that's correct. So which of these is or are nonmetals? So you would just have to look. So okay, cesium here, that's a metal. Vanadium is here, that's a transition metal. Oxygen is here. Let's get something you can see. Right, oxygen is here, xenon is here. They are nonmetals, right? So oxygen, xenon, rhodium, RH. RH is here, so it's a transition metal. So the correct answers there would be oxygen and xenon. Okay, so that's some basic terminology that you need to know. And so there's terminology associated with chemical reactions. So reactant means everything on the left of the arrow. So that's what goes into a chemical reaction. And then products, so these would be reactants. And then this would be the product. So product is whatever comes out of a chemical reaction. And then in chemical reactions, oftentimes we'll list the phase of the chemical or the element. So solid, liquid, gas, or if it's dissolved in water, an aqueous solution. Okay, and then the last thing that we want to do in this lecture is show you how to balance chemical equations. So basically what balance means is that all of the elements and numbers of elements that go into a reaction have to come out of a reaction. So however many oxygens you put in, that's how many oxygen atoms have to come out. However many phosphorus atoms go in, that's how many have to come out. However many chlorine atoms go in, that's how many have to come out of the reaction. So one consequence of this is a conservation of mass. Since all of the elements that go in have to come out, then mass is conserved in a chemical reaction. Whatever mass you put into a reaction comes out of the reaction. So that's true for a chemical reaction. That is not true for a nuclear reaction where some of the mass is converted to energy. But we won't talk about nuclear reactions in this class. That's covered in General Chemistry 2. Okay, so all of the elements that go in have to come out. So we want to have the same number of each element on both sides of the arrow, left and right. So right now we have 2 oxygens on the left, and we only have 1 oxygen on the right. So we need to have the same number on left and right. So what do we need to do? Could we put a 2 here? Now there's 2 on the left and the right. So is that the correct way to balance this equation? And the answer is no. You cannot do that. You cannot put a 2 there because that changes what the compound is. So the way that you would fix this is you would put a 2 here in front of the chemical compound. So that means now there's 2 phosphorus and there's 2 oxygens on the right. And there's how many chlorines? Well, you would take this and take that and you would multiply. So there's 6 chlorines on the right. And so you need 6 chlorines on the left. So how can you get 6 chlorines on the left? You can't change that number, right? That number has to stay the same. So what you would do is you would put a 2 here in front of the chemical compound. So now you have 6 chlorines and now you have 2 phosphorus. So now everything is balanced, right? You have 2 oxygens, you have 2 phosphorus, and you have 6 chlorines on the left. And you have 2 oxygens, 2 phosphorus, and 6 chlorines on the right. So that's a balanced chemical equation. So 1 O2 molecule, 2 PCl3 molecules react together to make 2 POCl3 molecules, right? So you have an O2, you have 2 PCl3s, and those react with each other to make 2 POCl3 molecules. So now you have the same number of elements on both sides of the arrow. Whatever went into the reaction came out of the reaction. Okay, let's take 2 more, 3 more. So N2O5 reacts to make NO2 and O2. Okay, so when you're balancing chemical equations, you should balance first the elements that appear in only one compound on the left and the right of the arrow. So in this example, you would not want to balance oxygen first, right? Because oxygen appears in 2 places on the right of the arrow. You want to pick elements that only appear in 1 place on both sides of the arrow. So we would start with nitrogen because it only appears in 1 compound on the left and 1 compound on the right. So there's 2 nitrogens on the left, so we need 2 nitrogens on the right. So we put a 2 in front of the NO2. Okay, so how many oxygens on the left? There's 5. How many oxygens on the right? Well, we would multiply those, so that's 4 oxygens, and there's 2 here. So there's 6 oxygens on the left, on the right, and there's 5 on the left. Okay, so how are we going to fix this? So let's see. So let's do this. So let's put 2 here. So now there's 4 nitrogens on the left, and so now we have to fix this. So let's erase that, and we'll put a 4 here. So now there's 4 nitrogens on the right. And now how many oxygens are there? Now there's 8 oxygens here, and there's 2 oxygens here, so that's 10 oxygens together. And 2 times 5, that's 10 oxygens on the left. So now that's a balanced chemical equation, right? We got 4 nitrogens on the left, 4 nitrogens on the right, 10 oxygens on the left, 4 oxygens here, and 2 more here, so 10 oxygens on the right, so that's a balanced chemical equation. Okay, so if we want to balance this one, so what element would we not want to start with? So don't start with the nitrogen because it's in 2 places on the right. Don't start with the oxygen because it's in 2 places on the right and it's in 2 places on the left. So that leaves you starting with the hydrogen. So we have 2 hydrogens here and we only have 1 here, so we would need a 2 here, right? Okay, and so what's next? So let's see. So how many nitrogens do we have now? We have 3 nitrogens on the left, and so we would need to put a 3 here. So now there's 3 nitrogens, and there's 2 hydrogens. And let's see, how many oxygens on the left now? There's 6 oxygens here plus 1 there, so there's 7 oxygens here. And let's see, 3 nitrogens on the left, right? There's 2 here plus 1 there. And there are 2 hydrogens. And there are 2 times 3, so that's 6 oxygens plus that one. So there's 7 oxygens, so that's balanced, right? So 3 NO2s react with 1 H2O molecule to make 2 HNO3 molecules and 1 NO molecule. Okay, let's take one more example. Okay, so what would we not want to start with? Don't start with bromine because it's in 2 places on the right. You could start with oxygen because it's in 1 place on the left and 1 place on the right. You could start with sodium because it's in 1 place on the left and 1 on the right. And you could start with nitrogen because it's in 1 place on the left and 1 place on the right. So if you start with an element that is in more than 1 places on the right or the left, your job is going to be much, much harder balancing the equation. Okay, so let's start with nitrogen. So we have 2 nitrogens here, so I'm going to put a 2 there, right? So now I have 2 nitrogens on the left and I have 2 nitrogens on the right. Okay, so now I have 6 bromines on the left. So I need to get 6 bromines on the right. So now we have to, okay, we could balance the sodium, but it's already balanced, right? There's 1 on the left and there's 1 on the right. Or the oxygen, there's 1 on the left and there's 1 on the right. So now we have to deal with the bromine because everything else right now is balanced. So 6 bromines on the left. How are we going to get 6 bromines on the right? Well, we could do 1 of these and 5 of these, right? That would be 6 bromines. Or we could do 2 of these and 4 of these. That would be 6 bromines. Or 3 of these and 3 of these. That would be 6 bromines. Or 4 of these and 2 of these. Or 5 of these and 1 of these, right? So there's 5 choices. So this makes it a little bit more difficult. Let's see. So how are we going to fix this? I guess, well, the way that you can solve this the way that I usually solve things. The way that I usually solve things is trial and error. I just start trying stuff until it works. So if you do 1 and 5, the problem is sodium and oxygen are in different molecules on the right, but they're in the same molecule on the left. So that means we can't do 1 and 5, right? That's going to make us do 3 and 3. If we had 3 NABRs and 3 HOBRs, then we have 3 sodiums and 3 oxygens. So if we put a 3 here and a 3 here, now we have 6 bromines. and now we have 3 sodium, and now we have 3 oxygens, and we have 3 hydrogens on the right. And if we put a 3 here in front of the NaOH, then we have 3 sodiums, 3 oxygens, and 3 hydrogens, and we are balanced, right? So that's the answer to that problem. 2 NBr3s react with 3 NaOHs to make 1 N2 molecule, 3 NABRs, and 3 HOBr molecules. Okay, hopefully that made sense. We will stop there.